Friends, to this lecture on NetSet Get Guidance. In this video, we are going to learn some questions on linear algebra part 2nd. Myself, Dr. S.M. Chinchole, Assistant Professor in Mathematics. First question, if T from R3 to R3 is the identity map, then nullity of T is equal to, options are 0, 1, 2, 3. See, when T from R3 to R3 is the identity map, it is the bijective map. As it is bijective, it is also an injective map, and as it is an injective map, its kernel is singleton 0 vector, and hence its dimension is 0. So the dimension of kernel T is nothing but nullity of T is equal to 0, and so the correct option is option A. Question 21. In which of the following alternatives a subset T of the set S is equal to set containing vectors 2 0 0, 2 2 2, 2 2 0, 0 2 0 is not a basis of R3 over set of real numbers R? Options are A. T is equal to set containing vectors 2 0 0, 2 2 0, 2 2 2. Option B, T is equal to set containing vectors 2 0 0, 2 2 2, 0 2 0. Option C, T is equal to set containing vectors 2 0 0, 2 2 0, 0 2 0. And option D, T is equal to set containing vectors 2 2 0, 2 2 2, 0 2 0. See, since 2 2 0 can be written as 2 0 0 plus 0 2 0, we can say that these three vectors are linearly dependent, and hence the set containing these three vectors 2 0 0, 2 2 0, 0 2 0 is linearly independent, and hence it cannot be a basis of R3 over set of real numbers R, and hence this is not a basis, so the correct option is C. Question 22. Let a1, a2, ... an be column vectors of size m. Assume that they have coefficients in set of real numbers R and they are linearly independent over R. Then option A, they are linearly independent over C. Option B, they are linearly dependent over C. Option C, they form a basis for Rm. Option D, they form a subspace of Rm. See, the column vectors a1, a2, an of size m are linearly independent over R is given, and hence for any n real numbers k1 k2 kn, k1 a1 plus k2 a2 plus ... plus kn an, this linear combination is equal to 0 vector implies k1 is equal to k2 is equal to ... kn is equal to 0, means for every linear combination is equal to 0 vector, the coefficients must be 0 because these vectors are linearly independent over R. And so, hence for complex coefficient alpha R is equal to kr plus ilr, we have alpha 1 a1 plus alpha 2 a2 plus ... plus alpha n an, the linear combination of vectors a1 to an with complex coefficients is equal to 0 vector in set of complex numbers, that is 0 plus I0, implies you can replace alpha 1 by k1 plus il1, alpha 2 by k2 plus il2 as alpha n is equal to kn plus iln, and after solving the brackets we will get alpha 1 a1 is equal to k1 a1 plus il1 a1. In this way we will get the expansions as k1 a1 plus il1 a1 plus k2 a2 plus il2 a2 plus ... plus kn an plus iln an is equal to 0 plus I0. If we take all the real parts together and imaginary parts together, we will get k1 a1 plus k2 a2 plus ... plus kn an as a real part plus I times imaginary part, that will be l1 a1 plus l2 a2 plus ... plus ln an is equal to 0 plus I0. And when we compare the real and imaginary parts on both sides, we will get k1 a1 plus k2 a2 plus ... plus kn is equal to 0. Real part of left side is equal to real part of right side, and l1 a1 plus l2 a2 plus dot 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 plus ln an is equal to 0. That means imaginary part of left side is equal to imaginary part of right side. Where k1, k2, kn, l1, l2, ln are real numbers. This implies we get the combination of a1 to an is equal to 0, where all the coefficients ki are real numbers, so we get kr is equal to 0. Similarly, for the linear combination of a1 to an with all coefficients l1 to ln as real numbers, we will get lr is equal to 0. 1 is equal to k2 is equal to kn is equal to l1 is equal to l2 is equal to ln is equal to 0, means all ki's and li's are 0, and hence ki plus I li, these complex coefficients alpha I are also become 0. That means this alpha 1 a1 plus alpha 2 a2 plus dot 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 plus alpha n an is equal to 0 with real coefficients alpha I if and only if all the real coefficients are 0. This implies that the vectors a1 a2 an are also linearly independent over set of complex numbers C, and hence the correct option is A. Question 23. Consider the real vector space over R3 and following of its subsets. S is equal to set of all triplets x y z belongs to V, where x is equal to y is equal to 0. Second, T is equal to set of all x y z belongs to V, where x is equal to 0. Third, W is equal to set of all x y z belongs to V, where z is not equal to 0. Which of the following statement is correct? Statement A, S, T and W are subspaces. Statement B, only S and W are subspaces. Statement C, only T and W are subspaces. Statement D, only S and T are subspaces. The only subspaces of R3 are, first is the singleton zero vector, that is also called as the zero vector space. Singleton zero vector in R3 forms a subspace of R3, which is also called as the zero vector space. Then lines passing through origin. Lines passing through origin means set of those vectors x, y, z in R3 where x is equal to y is equal to 0. These are the lines passing through origin. Planes passing through origin means set of all x, y, z belongs to V, where x is equal to 0 or y is equal to 0 or z is equal to 0. Here also x is equal to y is equal to 0 or y is equal to z is equal to 0 or x is equal to z is equal to 0. That are the lines passing through origin. Therefore, S is a line in R3, T is a plane in R3. So these are the subspaces of R3, and W is neither zero vector space in R3 nor line in R3 nor plane in R3. So W is not a subspace of R3 because W does not contain zero vector 0 0 0. Hence the correct option D, S and T are only subspaces of V is equal to R3. Question 24. Consider the real vector space R3. The subspace set of all x, y, z belongs to R3 where y is equal to x of R3 generated by which of the following set? A, set of vectors 1 1 0 0 0 1. B, set of vectors 1 1 0 1 0 0. C, set of vectors 1 0 0 0 1 0. D, set of vectors 1 0 1 0 0 1. The only vectors in the set 1 1 0 0 0 1 satisfies the condition of these subspace. These subspace containing those vectors in R3 whose first and second components are equal, and the only option set containing vectors 1 1 0 0 0 1 satisfies this condition where first two components are equal. So obviously this will be the correct option for this question. Also it satisfies the property of basis also. See, whenever we take the linear combination of 1 1 0 0 0 1 equated with 0 0 0, we will get alpha is equal to 0 as well as beta is equal to 0. So these two vectors are linearly independent in R3, as well as every vector x y z where y is equal to x can be expressed in the linear combination of 1 1 0 0 0 1 as y is equal to x, this xyz becomes xxz, and this xxz can be written as x times 1 1 0 plus z times 0 0 1. That means linear combination of vectors in this set. So this set is linearly independent in R3 as well as it spans this given set or subspace of R3. So it is a basis for the given subspace, and hence we can say that the given subspace is generated by the set containing vectors 1 1 0 0 0 1. So the correct option is option A. Question 25. If W1 is equal to set of vectors 0 y z w v, where y z w v are real numbers, and W2 is equal to set of vectors x0 z w v, where x z w v are real numbers, are subspaces of R5, then the dimension of W1 intersection W2 is equal to option A is 5, option B is 4, option C is 3, option D is 2. See, the set W1 intersection W2, it is nothing but the set of vectors which satisfies the property of W1 as well as property of W2. What are the properties of W1 and W2? W1 contains those vectors in R5 whose first component is compulsorily 0, and W2 contains those vectors in R5 whose second component is compulsorily 0. So the W1 intersection W2 contains all those vectors in R5 whose first and second both components of 0. So W1 intersection W2 becomes set of vector 0 0 z w v, where z w v are real numbers. So it is generated by three independent vectors, namely 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1. So its dimension is 3, and the correct option is C. Question 26. Consider the following assertions. Rank of St is equal to rank of S is equal to rank of T. Second, rank of St is equal to rank of S if T is non-singular. Third is rank of St is equal to rank of T if T is non-singular. Where S and T are the linear transformations from V to V of a finite dimensional vector space V. Which of these is or are correct? Option A is only first, option B is only second, option C is first and second, option D is second and third. If S is the null transformation, see, S and T are the linear transformation from a finite dimensional vector space to itself. See, if S is the null transformation and T is the identity transformation, then ST is also null transformation. Null transformation means image of every vector goes to 0 vector. It is a null transformation. If S is null transformation and T is the any transformation, then ST becomes a null transformation. Means image of any vector under S is 0 vector, and image of any vector in V under the T transformation is that vector itself. So it is identity transformation. While when we take their multiplication ST, it becomes again null transformation. Multiplication means the composition of S and T. So in this case, as S is the null transformation, its kernel is V itself. Its kernel is V itself. So its nullity is equal to dimension of V, and its rank is equal to 0. So similarly, rank of ST is 0. While rank of T is equal to dimension of V and kernel of T is equal to singleton 0 vector, means its nullity is 0. So what we get? Rank of ST is equal to rank of S is equal to 0, and rank of T is equal to dimension of V. Means in this case, we get rank of ST is equal to rank of S, where T is the identity transformation. T is the identity transformation means it is non-singular. It is invertible. Okay. So the option second is correct. Rank ST is equal to rank S if T is non-singular. While rank ST is equal to rank T, it is wrong if T is non-singular. In the same case, T is non-singular, but rank ST and rank T are a different one. Okay. So the second option is correct, third option is wrong. And again, if we observe first option, rank ST is equal to rank S equal to rank T, this is also incorrect in this case. So the only option second is correct, and this is justified by this particular example. So the statement first and third fails. Correct option is option B. Question 27. The matrix of the linear mapping F from R2 to R3 given by f of xy is equal to 2x comma y comma x minus y with respect to the standard basis is, option A is matrix 3 by 2 matrix 2 0 1 0 1 minus 1. Option B is 2 by 3 matrix 2 1 2 1 1 2. Option C is 2 by 3 matrix 2 0 0 1 1 minus 1. And option D is 3 by 2 matrix 2 2 1 1 1 2. See, the standard basis for R2 and R3 are 1 0. Set containing vectors 1 0 0 1. This is the standard basis for R2. And set containing vectors 1 0 0 0 1 0 0 0 1. This is the standard basis for R3. And for the linear transform f of x y is equal to 2x y x minus y, we will get f of 1 0 is equal to, just we have to replace x by 1 and y by 0. So we will get 2 times 1 0 1 minus 0, it will be 2 0 1, and this can be expressed as the linear combination of standard basis vectors 1 0 0 0 1 0 0 0 1 of R3 as 2 times 1 0 0 plus 0 times 0 1 0 plus 1 times 1 times 0 0 1. Similarly, the image of second standard basis vector of R3 under this function f is f of 0 1 is equal to, we have to substitute x is equal to 0, y is equal to 1, so it will be 0 1 0 minus 1 is minus 1, so 0 1 minus 1. It can be expressed as the linear combination of these standard basis vectors of R3 as 0 times 1 0 0 plus 1 times 0 1 0 plus minus 1 times 0 0 1. So the matrix of linear mapping becomes 3 by 2 matrix. Just we have to write the coefficients column wise. Means here we have the coefficients of f of 1 0 as 2 0 1 and coefficients of f of 0 1 as 0 1 minus 1. You have to write this 2 0 1 0 1 minus 1 as column wise, and we will get the matrix of transformation as 3 by 2 matrix 2 0 1 0 1 minus 1. So the correct option is option A. Question 28. The dimension of the space of n by n matrices, all of whose components are 0 except possibly their diagonal components, is, option A is n square, option B is n square minus n, option C is n, option D is 2n. The vector in the given space contain at most n non-zero diagonal components because it is the space of n by n matrices, all of whose components are 0 except possibly diagonal components. Means all the n square components of matrices except n components, possibly n components, are 0. So the vectors in this space contain at most n non-zero, that means diagonal components, and the total components of n square. So its dimension becomes n, and the correct option is C, because to represent such space we required only n elements which are nothing but the diagonal components of that matrices. So the correct option is C. Question 29. For a fixed positive integer n greater or equal 3, let A be n by n matrix defined as A is equal to I minus 1 upon n times j, where I is the identity matrix and j is the n by n matrix with all entries equal to 1. Which of the following statement is not true? Option A is A raised to k is equal to A for every positive integer k. Option B is trace of A is equal to n minus 1. Option C is rank of A plus rank of I minus A is equal to n. Option D, A is invertible. For n is equal to 3, we can get A is equal to, I is the identity matrix 1 0 0 0 1 0 0 0 1 and j is the matrix with all entries 1, that means 1 1 1 1 1 1 1 1 1. So we will get A is equal to 1 minus, see, A is equal to identity matrix minus 1 by 3 times j. So 1 by 3 times j means it will be 3 by 3 matrix with all entries equal to 1 by 3, and identity matrix is 1 0 0 0 1 0 0 0 1. So A becomes 1 minus 1 by 3, 0 minus 1 by 3, 0 minus 1 by 3, 0 minus 1 by 3, 1 minus 1 by 3, 0 minus 1 by 3, 0 minus 1 by 3, 0 minus 1 by 3, 1 minus 1 by 3. So it becomes A is equal to 2 by 3 minus 1 by 3 minus 1 by 3 minus 1 by 3 2 by 3 minus 1 by 3 minus 1 by 3 minus 1 by 3 2 by 3. So this square of this A is A square is equal to A into A is equal to, when we multiply these two matrices we will again get the matrix A itself. So A square is equal to A, means A is an idempotent matrix, and hence as it is idempotent matrix, a square is becomes a cube becomes a raised to 4 becomes a, so a raised to k is equal to a for every positive integer k. Moreover, trace of a is equal to summation of 1 minus 1 by n, because identity matrix contains only diagonal elements is equal to 1, all remaining are zeros, and the trace is nothing but the sum of diagonal elements, means trace of a becomes sum of diagonal elements of a, which are nothing but 1 minus 1 by n times 1, so it will be 1 minus 1 by n, and such diagonal elements are n in number, so it will be summation of 1 minus 1 by n I is equal to 1 to n, so it will be n times 1 minus 1 by n. It is equal to n into 1, that is n, minus n into 1 by 1 by n, that is 1, so it will be n minus 1. Rank of a, it is equal to n minus 1, as any row or column of a can be written as negative of sum of remaining. Any row or column of a can be written as negative of sum of remaining, so 1 is dependent on the remaining and remaining are the independent. Remaining are independent means n minus 1 of the rows as well as columns of matrix A are independent, so its rank is n minus 1. Also, rank of I minus a is equal to 1, as all rows of I minus a are non-zero and same. When we take I minus a, then its rank is 1, because its only one row is non-zero. As all rows are non-zero, when we reduce it into row echelon form, its only one row becomes non-zero and all remaining becomes 0, so its rank is 1. So rank of a plus rank of I minus a, it becomes 1 plus n minus 1 is equal to n. And fourth is, as the rank of a is equal to n minus 1, determinant of a becomes 0, and hence a is singular or non-invertible. So the only option D is correct and all the remaining options are incorrect. Thank you. If you have any question, you can find me at mrsanjaymas@redifmail.com as well as mrmas@gmail.com.